Okay, we've come to section 4.7 on applied optimization. So the point of this section is that we're going to apply the optimization techniques, trying to find the minimum and maximum values of a function on some interval, to various applied problems, real-world problems. So for instance, we might say we want to maximize the profit of our company. We want to minimize travel time. We'll want to maximize how big of a fenced-in pen that we can build for some animals, stuff like that. So just as a reminder of how we do optimization, how we carry out optimization, if we have a continuous function and we want to optimize in a closed bounded interval, we find the critical points of your function in the that lie in the interval, and then you evaluate f at the critical points and at the endpoints, and then you're able to pick the maximum and the minimum. So we know our theorem guarantees that we have a continuous function on a closed bounded interval. It's guaranteed to have both a min and a max, and the only places that the min and the max can occur are the critical points and the endpoints. So let's just so what we're going to do right now is just focus on, we'll have these problems. These will be the computational steps, and we'll just have one step before we get there of setting up the problem in the first place. So let's take a look at a problem of this kind. So a piece of wire of length L is bent into a rectangle. So which dimensions produce the rectangle of maximum area? So the idea here is that we have this piece of wire of length L, and we are going to bend it, and so the total length there is L, and we're going to bend it into a rectangle, and our goal is we want to try to make the area as big as possible. So that's our goal. So at this point, what we have to do is we have to write down a function that we'd want to maximize here. So we know we're going to want to maximize area. So let's label this x times y. So we're trying to maximize x times y here. So right now, this is actually, there's two variables going on, x and y. When you go on to take multivariable calculus, you actually will learn more about functions of two variables. But this isn't good for us right now. We want to get rid of one of the variables. And so the thing to realize here is that, these two sides must be y, these two sides must be x. Think about what relationship we have between all of these variables. And so x plus y, that must equal the total length L. So that's 2x plus 2y is equal to L. And we want to now solve for y in terms of x. And so we solve for y in terms of x. We actually end up with y is equal to L over 2 minus x. So hooray, we can take this and substitute in here. So now we see that we have a function a of x is a function of x is equal to x times L over 2 minus x. So we have a function, we want to maximize this. Now let's just take a moment to think about what is the domain. What's the domain of x here? What's the biggest and smallest x can be? And so a bit of thought should convince us x can't be negative. The smallest x would be 0. And the biggest x would be L over 2, because that would be putting all of L onto one side. So if x is equal to 0, that's basically making all of L on the two y sides. If x is L over 2, that's basically making all of L on the two x sides. Now you might say, well, it's a rectangle of, 0 width or 0 height or something like that. You may say, well, that's a little bit weird. It's okay, we can handle that till I have 0 area. That will be okay. So this is where we are for our problem. we're at a point where we basically have our function a of x is x times L over 2 minus x, and our domain is 0 to L over 2. So at this point, our goal is just to crunch through the steps from before, find the critical points of the function in the interval, evaluate the function, the critical points, endpoints, and pick their maximum and minimum values. So let's do that. I'm just going to go ahead and rewrite that. Remember here, L is a constant. L is like we have 100 feet of wire to work with. L would be 100 in that case. Okay, a prime of x is L over 2 minus 2x. And we want to find critical points. This will never be undefined, so we set it equal to 0. And what do we end up with when we set it equal to 0? X is equal to L over 4. This is the only critical point. So now we found all the critical points. There's only one of them. We want to evaluate a function, the critical points at the endpoints. So a of L over 4. We'll also do a of L over 2 and a of 0. So we plug in all of these, a of L over 4, plug in L over 4 up here. After crunching things out, you end up with L squared over 16. And you plug in L over 2 or 0 up in here. It's pretty easy to see that you'll get 0. So what's our conclusion? This gives the maximum value, and these two both give the minimum value. And so I'll just point out here, if for the maximum value case, if x is equal to L over 4, y is equal to, remember what y is? Y is L over 2 minus x. And y is also L over 4. And so what is our best case? How to make our rectangle as big as possible? Make it a perfect square, where all 4 of the sides are L over 4. That will make the area of our rectangle as big as possible.